Me and Bernardo, we will talk about iBoot when U-boot. We basically did some research in U-boot-based bootloaders, bootkits in this case. And we're going to talk about what we did. So first, we will have an introduction. We talk about ourselves, what we do, who we are. And then we're going to talk about malware that already exists for embedded devices. Then we'll talk about the boot process of an embedded device, how it works. And then how we gain persistence on an embedded device, in this case on U-boot. Then we're going to talk about writing a bootkit and then about how you can mitigate and detect these type of bootkits. So my name is Vincent. I work in the KPN Red Team. We're located in Amsterdam. I used to work as a consultant, but now I'm a happy Red Teamer at KPN. I'm also moderating for New Amsterdam. It's a community chapter. So if you ever come by Amsterdam, you have a topic to talk about, feel free to contact me and we can organize something. Yeah, you can.
Yeah, so my name is Bernardo. I'm Brazilian, so I can probably give this talk in Portuguese, but I'm going to stick to English. I'm also based in Amsterdam. I work for KPN, which is a telco for the KPN Red Team. I'm a big Bruno Aleixo fan. You guys know Bruno Aleixo? Yeah, Bruno Aleixo is awesome. And yeah, sometimes I play CTFs with the Goonies, which is a Brazilian CTF team. And I'm really good at breaking routers. So if you need any advice on breaking your devices, you can just ask me. So I will start talking about malware on embedded devices. Yeah, spoiler alert, it's nothing new. So Mirai, I think most people heard about Mirai, which was just like scanning the internet, finding devices with like hard-coded passwords, infecting them. And Mirai, for example, it doesn't care about persistence. So Mirai will just like hack a device and like if it doesn't care about persistence. So if you just reboot the device, the malware is gone. So, and it's so fast for it because it's constantly scanning the internet. It's so fast. Your device will get, after you reboot, your device will get reinfected really fast. There are like other malwares, like LuaBot was targeting also cable modems. I posted a write-up about it. The Moon. Some of those malware, like the Karna as well, is a really interesting one, which was one of the first malware that would try to like scan the internet as a whole, infect embedded device, and also start scanning. And like an anonymous researcher posted all the results from the Karna botnet. So he wrote like a paper after infecting lots of devices, malware, and he wrote a malware that would infect embedded devices, and he wrote like, started scanning the internet with all those malware. But also like Flasher.a and the CIA Cherry Blossom. So the Flasher.a, which was something more focused on German. And this malware would exploit like a command injection on DDWRT, which is an open source firmware for like routers. And then it would reflash the firmware with a modified DDWRT. And this modified had things like dsniff, things like that they could sniff passwords in plain text, which were going through the network in plain text. And also the CIA Cherry Blossom, which is also interesting. It's more of an implant than a malware. So because the CIA operates kind of different from NSA. NSA is more like signals, intelligence, and remote things. And the CIA, because they would just go to your house and implant things. So which is the CIA Cherry Blossom, it's on Vault 5 WikiLeaks documents. But it's like basically also modified DDWRT, OpenWRT images with like toolkits and everything they need to infect your embedded device.
Now I'm going to talk about the boot process of an embedded device. So the moment you turn on your embedded device, it jumps to like the NOR flash, and it contains some bootstrap code and initializes some hardware, does a post, and then it un-LZMAs the bootloader into RAM memory, and then it jumps to the bootloader. The bootloader then also initializes some extra hardware, does some other post checking, and finds the kernel and decompresses the kernel into RAM memory, then jumps to the kernel. And the kernel then takes over, and the kernel does initializes some file system kernel modules, so you can actually mount the file system of your embedded device, then runs init on the file system, and your device is running. And here you have a nice graph. You have the bootloader, does some post.
To the left.
Oh yeah, to the left. Sorry, to the left. So I'm a left guy, so it's fine. So here would be some bootstrap code for un-LZMAing the bootloader, and it like jumps to the firmware. LZMA compresses the kernel basically, and becomes the operating system, and then that's basically it.
So what are the advantages of like getting a persistent on a bootkit level? The first thing, it's very interesting, like firmware upgrades, they normally won't mess with the bootloader because it's very easy for you to mess. So For example, you have like an Asus devices and Linksys, and you go to the vendor website, there's an update. So, I don't know, crack, the new vulnerability, so you have to upgrade your firmware. So you go to the Asus website, you download the new firmware, and you go to the browse to your router settings, and you upload a new firmware. And most of the times, like this new firmware would only change like the partitions related to actually like the firmware file system, and the bootloader won't be changing at all. So if you have like a persistence on the bootloader level, if someone reflashes, if someone like restores to factory default, then you still have like that modifications on U-boot settings. And it's also very difficult to detect. So like most security teams are kind of not ready to detect this. And it also bypasses operating system security features, which on embedded devices cases, it's like nothing. So, but yeah,
security, what?
It's still bypassing.
Yeah. It's also very specific to your system on chip to write a bootloader, a bootkit, because every system has their own variables and their own the chip drivers and everything. So it's kind of hard to write one.
So yeah, disadvantages. So it's really cool. So you have persistence. Sometimes you may mess things. So on the Snowden documents, there's like this news. NSA accidentally caused Syria internet blackout in 2012. So what NSA was doing, they like had all those implants, all those switches from Syria, and they all wanted to like wiretap the internet. They want to also like run commands. They want to see traffic from that country. So they had issues while upgrading the firmware or doing something like that, and the device, like the whole internet, stopped working from the country. You can always blame like other things, but it's something difficult for you to maintain. So every device is different. If you're changing the bootloader, you may break the device. So it's difficult. It's something more sensitive.
So there are different ways to get persistence on embedded devices, just like on a regular Linux system. You can change the init scripts. So you mount the file system, you add some code to an init script, or you add a binary that gets kicked off by init. You can also create a loadable kernel module. You can modify the UEFI BIOS, or you can change the NVR or VBR records. What we do, we'll talk about it later.
So yeah, we're talking about bootkits, and again, bootkits are nothing new. So there are like known bootkits so far, things like Mabroot, Rodrigues, Bromi, and some of those bootkits are also targeting Linux. It's the case of the old boot. So if you Google online, there are like some write-ups about it, and people are not exactly sure if it's like from APK it infects your bootloader, or if it's like a firmware implant, like the vendor was already infected. So if you need to change the bootloader code, you have to have root on the device. And this was basically a modified bootloader that would do like it to act as a Trojan. And also it's very interesting, the hacking team, UEFI. So it's more like an implant. And I wrote there that it's an implant, and the method of infection is Surge, because, Surge is like a guy working for the hacking team. And while they had demos and POCs for like their clients, and he would just like fool the clients and like disable antivirus while he was like infecting devices and making demos. So he's kind of the infection mechanism. So the hacking team, RK Loader, there's a really cool write-up from the Intel guys. What it does, it puts like files, while you're loading the file system, your NTFS file system on Windows case, it would load a binary. And if you format your Windows install, the UEFI, if it's backdoored, it would download the code and run again. So there are like different methods. So some motherboards, some laptops, they had like some vulnerabilities. For example, the write protection is not enabled. So you could remotely, so if you get root on a machine, you may rewrite some variables or something, and then you can put the hacking team backdoor there. But sometimes when this is not possible, if you have physical access, you can open the device and you can dump the SPI, and you can rewrite the SPI with new settings or with the backdoor content. So, is it me?
Yeah, it's you.
iBoot when you boot, which we wrote. It's kind of like a bootkit targeting U-boot and embedded devices using U-boot. And U-boot is like an open source bootloader. And we need an initial access. So we're just like, we can infect a device if we have physical access, or we can infect the devices remotely. And we were thinking about something like, we want root on a machine, and we want to change the bootloader. We want to change this partition. So we need an initial exploit. Go back. And yeah, some examples of exploits that we can use. It's like the Samba cry, which is like if you can save a file to a Samba share, and you can put like a library there and load command injection, like ping command injection. Most routers, they have like command injection, and they also don't segregate privileges. So if you're able to find an exploit for an embedded devices, like 9 out of 10 times, you always get root, and then you can start like gaining persistence. So Linux kernel the MTD memory. So you have like the flash chip from your router, and the name they use, it's like Memory Technology Device, MTD. There's a file system on the top of MTD. So the kernel, the Linux kernel, it says like, it defines when each partition starts and ends. It's not like you have your hard drive and you say like, this is starting partition 1, here are the details, and here's partition 2. It's not like that. It's like the kernel is defining. So if you look, if you get /proc/mtd, for example, it's going to say like, from this offset until that offset, you have the U-boot partition, then the kernel, rootfs, art, firmware, and all those partitions. And what we want to change, what we want to infect, is the U-boot partition or the bootload partition, which is like the first one most of the times. So the boot partition is commonly mounted as read-only. So the MTD0, on that case, on the U-boot partition, it's mounted as read-only. So we have root on the kernel, on the machine. How can we change that if it's read-only? If the kernel is explicitly saying, this is read-only, you can't write here. So we have to think about some way to bypass that. So if you get the source code, you see like it's RO. There's this kernel module called mtd-rw, which is basically a Linux kernel module. And I can tell the kernel that to like switch that flag. So if that partition was read-only, I just use like insmod. I load the kernel module and say like, this partition is not read-only anymore. So then I can write. So if we go to the next slide, this is the source code from mtd-rw. It is just checking like, it's just checking how are the flags, and it's hard coding, telling the kernel, these partitions are, I can also write on them. So
yes, it does a binary OR here, and then to disable it, it does an AND NOT. So just to unset the flag.
And yeah, so this is the example of if you have a root shell, you just like, the first thing you also need to do, you will need to cross-compile this kernel module for your platform. So if you're working with a MIPS device, little endian, you have to cross-compile for MIPS. If you're working with an ARM device, you have to cross-compile for ARM. So you just like insmod the module, and then there's like, insmod, I want a brick equals 1, because most of the times you're going to mess, and we're going to show you why. And you just put mtd write, U-boot, you have like an image, and it's just like a dd command. So mtd write, it's quite similar to dd. You can also use dd to just write to that partition because it's not read-only anymore. And then we reboot the device. So now, after the device boots, you have a different bootloader.
So now we're going to talk a bit about writing a bootkit. Just like we said before, all hardware devices have different settings in bootloaders. So what we did, we downloaded an open source project called U-boot mod, and we got a device that was already supported, so we didn't have to do any of the hard work. And also interesting is that devices running U-boot, they have a GPL license. So it means that if you have a device running U-boot, you're legally obliged to supply the source code to anyone who's requesting it. So what you could do is you could write a letter because they want letters, and then you could request a source code for a device that runs U-boot, and they might send it to you in the mail after a year or two.
It's very interesting because lots of those vendors, like embedded device vendors, they offer the option because they have to, but you can't just download from their website. They're like, if you really want the source code, you have to send us a letter, like you manually write to us, you send us, and then we're going to send you the source code.
I think the EFF also assists you if you really want the source code.
If you have an issue with that, like GPL violations, you can always also contact EFF.
So, because we are going to break our device maybe 10 times, a soft brick, we had to make some preparations to the device. So we have a colleague who used to solder motherboards when he had a part-time job. So he can solder really well. What we did here, we desoldered the SPI flash chip, and on where the pins of the chip, he soldered some wires. And then we used a chip programmer, I don't know how you call that, a SOIC, or a chip programmer attribute, and put it on there. So he just reads the chip. So when you boot on the device, it just boots regularly. But the moment when we brick it, because we made a mistake, we can just put it in a chip programmer like here. And then we can just put back the original bootloader.
It's also interesting to mention, if you have a Raspberry Pi, or if you have a BeagleBone Black, or like an Arduino, all those devices you can interface with SPI directly. So you can use like either a good FAT, you can use a Raspberry Pi directly, and then you can interface with SPI, and then you can rewrite as well. So it's not like you have to have a programmer or anything like that.
This is a good one. It's kind of cheap, but it's from Iran. The software might be a bit dodgy, so run it in a VM. But it's really good. It has a lot of support, keeps adding new support, and it's like $500 or something.
So why U-boot? So why did you focus on U-boot? There's this website called WikiDevi, and this website, it lists like hardware information from like home routers, webcams, and all those things. And I did like a small scrapper, and like I saw that U-boot is used by most devices use U-boot. And the second most used one is called CFE. It's called Common Firmware Environment. So this bootloader is proprietary. It's from Broadcom. So mostly Broadcom devices, they have CFE. But sometimes it's also interesting that some devices, they have like more than one bootloader. So they have like CFE and U-boot at the same time. And for example, some SOIC, some system on chip is using one, and the other system on chip is using another one. It's also common to happen.
So U-boot is basically on the first entity partition. And it basically has a code block and a defined area for environment variables. And depending on your device, the environment variables, which will be stored at the end of the U-boot partition, it's not actually a partition, but the size might be different. So you have some require more environment variables, so the size might be smaller or larger. And here you can see, like in Rodrigues, where the environment variables are. Here's like the data section, a couple null bytes, and here you can see that it's basically a null byte separated list of environment variables. This is what you see after LZMA decompressing the U-boot, which you dump from a device. You can change some environment variables here. So an interesting one is like the boot args. In some cases, you can change init. Instead of like as bin init, you can change to bin bash or bin sh. You can get a root shell. But at the end here, there's like a small checksum, a CRC32 checksum that checks for the validity of your, the corruption of your environment variables. So you need to change that as well. There are some interesting functions in U-boot. You have like printEnv, which prints the environment variables, TFTP boot, which is responsible for booting a device from TFTP. And then we have the env stop string, which is a password protection, but not really a password protection for U-boot. And you have bootcmd, which is the first command that U-boot will execute after the device has booted. And the ping command, which is just an ICMP ping command like on your Windows device or Linux. Also interesting is that U-boot has a scripting language, which kind of looks like bash. Over here we have a dual boot example, which we will show you later. We do a ping to see if a server IP, which is an environment variable, is live. If that server is live, then it will TFTP boot from a load address, which is also an environment variable, a file called backdoor.bin. And if it's loaded, then it will boot the load address and jump to the kernel for backdoor.bin. And if you can't ping the device, we just boot the regular firmware that's already on the flash chip. And printEnv is interesting because it does a loop through the null byte separated list and just prints environment variables. And if you want to add some malicious environment variables, we want to patch that function. So that's what we did. We wrote an extra function, like a function or two, and here we go to the null byte separated list, and then we find a match for the variable. So we have like bootcmd, for instance. It's interesting to backdoor because you can change to bin bash, or I think we did bootcmd, we changed it so that you can actually dual boot the device. So what we do is we find a match and see if it wants to print bootcmd, and if it wants to print bootcmd, we set a flag, and then we print like the hard-coded fake environment variables there. And bootcmd is the first command that executed when the device boot. It's actually a U-boot script command. So it's usually an environment variable, but you can override it in source. So what we did, in our bootloader, we just hard-coded the bootcmd dual boot command, which you can see right here. This is like a if-defined config boot command. gets it from it set as an environment variable, and then when it's booting the device, it gets the environment variable, and we override it right here because we just wanted to boot our malicious dual boot. Now we're going to show you dual booting the device. Let's see if I can get I'll do that over here actually. It's easier. Oops. Yeah. Stuff happens always like this. So. Okay, so you see 3 screens here. This one will be a screen session of a serial to our device. Over here, there's a command for setting up a TFTP server. And over here, we will ping the TFTP server. So we will boot the device, and then we will we will boot the device without having a server set up. So it will boot the normal firmware on the chip. And then afterwards, we reboot the device, and we start the TFTP server, and then see if our device will dual boot our maliciously created kernel. So as you can see here, the destination host is unreachable. It's not live yet. So we wait, press enter, and here we have like standard OpenWRT. And we start the TFTP server. There's a sleep in there because we had some issues. Now you can see the TFTP server is live. And we patched the TFTP boot command so it doesn't show you that it's actually TFTP booting. So there is a delay here, which is kind of odd, but not a lot of people look at the device booting on serial. So it's kind of stealthy, I guess. And successful transfer. And now we wait and press enter, and then did I press enter here? What's happening? Oh, there you go. And we dual booted our malicious.
And on this specific case, we're just changing like etc MOTD, message of the day, but we can change init start new files or anything like that. And it's also interesting to mention that we have a server. So why did we were pinging that server? So suppose I have an implant at like any location. When you boot the device, the U-boot already has a TCP stack. So you can ping hosts and you can do like TFTP, or you can also do FTP, wget, doesn't matter. You can, it's C code, so you can do whatever you want. And you also have a TCP stack. So we keep pinging a server. We control the server, and it's a malicious server. If we suspect that someone is, I don't know, trying to analyze our thing, our bootloader, we can just turn off the server. So this ping won't succeed, and it won't download the backdoor kernel.
And it's also in ROM memory, so we don't actually write it to ROM. So if you don't want to lose your Uber lead hexing tools, then this is a...
And if you reboot the device and the server is not online, it would just boot the regular image, nothing at all, like the firmware partition, there's nothing changed.
So the password protection I spoke about earlier, it's like an environment variable. So if you run strings on the device after dumping the flash, you can see the password. Sorry, I need to use air quotes here. It's hidden from the user, So what we did here is that, the env stop string is actually for people who don't want people to look inside their bootloader. So vendors sometimes do this because they don't want you to get root on the device. And if you can change the environment variables for bootcmd, you can get root on the device. So I think TP-Link has a env stop string called TPL, which is really easy. But anyway, what we do here is if you fail to enter the password, we will wipe the device. So we put a bootcmd in there, like erase all, reset. So if you press enter, for instance, then that's not part of our password, so it will wipe the device. And we have a demo where we do exactly that. Because most people, we also patched, as you will see here. I'll show that later. When a device boots, everything is fine. Green light is blinking. You see, the D message basically.
And it's also interesting to mention that this is a serial console. So when you boot a device, you are not seeing this at all. You just wait, and then you connect to the web server. So if you connect the wires and serial, if you find a serial connection, then you actually see this.
You can only see this on serial. So now we are rebooting the device, and it says press a key. And the moment you press a key, then it will wipe the device. So we want no one to look inside the bootloader. Okay, go back. So what we also did to hide from strings, let me get this. To hide from strings, what we did is we didn't hard code the stop string inside. Yeah, we kind of did hard code the stop string, but not as a string, but as a string array. So when you compile this after doing a string copy and a malloc, it will look like this. It's a very simple obfuscation technique, but yeah, it prevents people from running strings and seeing your password. It takes a little bit more effort to find out the stop string. So what we will now show you is how you can bypass the stop string protection. Because when the device boots, U-boot is basically in memory. And then just like between loading the kernel from the flash, there is like a small time frame where you can glitch the data out pin. And when you can glitch the data out pin, preventing the Linux kernel from being loaded in memory, you can fall back inside the bootloader, because the bootloader is already loaded in RAM memory. And the blue wire here is the data out. And as you can see, it just falls back into U-boot. So it's kind of useless as a password.
And if you Google, if you like search, for example, password protect U-boot, there are going to be lots of references like, yeah, just use stop string. But it's not like a security feature. It's just like some kind of protection that's not like really a protection. And also like some people, some websites, they use this method for you to, if you need to root your device. So if you have like a webcam and you can't get the U-boot console and you can't get access to do, because if you have access to the U-boot console, you can rewrite things, you can dump the whole firmware, you can do lots of modifications. And sometimes they lock the U-boot, they don't want you to mess with the firmware at all, so it's like you don't have an option. So this is like a really simple technique that you can use to bypass this protection and then like get to the U-boot console. So now I'm going to talk really quick about like detecting bootkits. U-boot, thinking more about like U-boot, but U-boot nowadays it has reproducible builds. So what does it mean? So if I compile some C code today, and tomorrow I compile like the exactly same code, the compiler is going to put like some garbage there, things like, I don't know, GCC version, like sometimes timestamps and all those information. And U-boot also has this issue. So if you compile it, it's going to hard code some dates over there. So there's this variable called source date epoch. So it's going to be like a fixed date. It's going to be like the epoch date. And if you compile the same code today and tomorrow, it's going to they're going to both have the same MD5. And it's also interesting to note, Debian, for example, they have that for their packages. So there are like reproducible builds. So you can get a source code and you can use like compile that with like there's like code that you can just download from Debian servers, try to compile, and you can check if the DPKG matches like the deb actually matches with the MD5 from the SHA-256. It matches with the one you compiled. So, and also like detecting bootkits, there's this tool called chipsec. It's more focused on like not focused on U-boot. It's more like on laptops, and it's from the Intel guys. And what it does, it's like it has a series of checks. So it's gonna check, for example, if I don't know, you can write variables on your UEFI partition. It has like several pre-made checks. For example, they can detect the bootkit from UEFI. They have like some signature checks and some stuff like that. And there's also this repository, which is really interesting. It's called known UEFI executables. It's also from the Intel guys, which you can just like get hashes from different motherboards or laptop. Like if you buy an Asus motherboard or an Asus laptop and you like dump the SPI, like the UEFI content, then you can also compare that with like from the full factory from that version. So it's not like really easy because you can't just take the MD5 from one and like the MD5 of the other ones. You have to ignore like the variable partition sometimes because it's tied to like each device. So yeah, this is just like a screen of if you run chipsec. In this case, it's on a MacBook, but it says like, yeah, chipsec modules, common BIOS write protection is not enabled, which means like you may write things to the BIOS. So you may need to check if you want to do any hardening on your BIOS. You can try to change some settings. And there's also this really interesting presentation from the Google security team. It's called firmware biopsy. And it's really interesting because they mention like some of the challenges. And what I mentioned, like firmware, granularity, and visibility. Very few companies, they have visibility of like what they're, what people are actually running on their devices. And it's not, just as I said, it's not like just hashing something and comparing hashes. Because like there are different environment variables, and you don't know, for example, each vendor, they put that on different sections. It's not like something standard. So, for example, if you think about like home routers, and you check the the BIOS, the bootloader partition, and the bootloader partition, your router and from another person, they probably have different MAC addresses. So you have to ignore that section. So they also have different settings on the bootloader. So you have to ignore that. And it's not like easy to parse that because you have to write parsers for different vendors. And also like unpacking the firmware, because different firmware, they use different compression, and it's not like a standard. That's also something that's very difficult. And like, yeah, there's this people talking on Twitter, like continuous assurance of performance is also crucial. If your EFI secure boot suddenly started silently booting unsigned images, would you know? Like very few people would just know that, because we don't have inspectable systems. So that's how our Flake is mentioning on Twitter. So sometimes we also have not so trusted computing. Also on these Snowden documents, there's like some pictures of NSA actually intercepting packages. So suppose your company is buying a new switch. So they were actually implanting them. So they were intercepting the shipment, and they were implanting them. And so it's difficult for you to know what's running on your device nowadays. So there's also supply chain attacks. Did you guys hear about the CCleaner hack? It was like last month, or that was really recent. So the CCleaner hack, people say, like the experts say it's China. It's always either China or Russia, but
probably FireEye.
And China, they said that they hacked CCleaner servers, and they were selectively infecting, sending a second stage payload depending on your host name. So if your host name contained, like for example, one of those entries, they would send you like an additional payload, which means you're on the corporate network of those companies. So if you're either running a backdoor CCleaner from, I don't know, VMware network or Cisco or Linksys or the Link.com network, they would send you a second stage. And people, if you stop to think about like Linksys, Cisco, and the Link, they sell lots of like home routers as well. So they're actively trying to actually either get source code, in fact, more devices. So what if they implant like the firmware from those vendors? We have no idea. And people don't care about checking that at all. And also, like, do vendors get hacked? So this is a screenshot from the Link Brazil and the link.com.br. And people are actually, they put like a JavaScript to mine Bitcoins on your, like.
Weren't you in Brazil 2 weeks ago?
Yeah, it was like last month.
Pretty complicated.
So what happens here, like, if you have access to the web server, you can also replace the firmware images, and you can put like a backdoor image. So people who are downloading like images, you have no idea. So it's like so easy for them that instead of backdoor firmware, they just like, so easy. I'm gonna mine crypto coins using JavaScript. And also there's this vendor called OpenMesh, because of requirements from FCC. So if you're selling a device in the United States, there are like some rules that you have to follow, otherwise you can't sell those. So if your device operates on the 5 gigahertz frequency, you have to put some lockdown that people wouldn't be able to change to certain frequencies because of FCC. So if you don't put lockdown, you can be sued. So FCC might sue you. So there's this vendor called OpenMesh. They were like, oh, okay, so we need to be compliant. So what do we do? Let's protect our U-boot. So OpenMesh, they sell like repeaters, small home routers, all those things. So what they did, they put like a signature. So you can only sign U-boot images. So there was like this check, and they were using RSA. So they had the private key, and they were signing the U-boot image. So if you try to modify or change anything over there, you can't bypass that and change for example, your firmware to enable different frequencies. So those researchers, what did they do? They just, because it's GPL, they asked for the source code from the U-boot. So they got the source code, they analyzed, and they found out that if you if you zero out the public key inside the U-boot partition, it's not going to check it anymore. It's going to boot anything you want. So it's a simple hack. So if you have a root on the device, you can DD on the offsets from the signature. And because there's no signature, it just fallbacks to booting any U-boot image you have at all. And they also found this interesting bypass as well. So when you TFTP boot images, so they have like, this device also have a recovery mode, which you can use like a signed image to download to boot and recover your device. So there is a Stack Overflow on the TFTP boots. So when you issue a TFTP boot command, it's going to download something from a TFTP server. So it doesn't care about the size of the image. So if you download like a huge image, you're going to corrupt the stack. So and that's it. You can use that to actually fall back to the U-boot console. But it's kind of more complicated because you need a JTAG debugger in order to do this, to find this properly. There's also some really interesting talks about the Rescue guys. So about like bypassing security protection. So they gave a talk recently on SHA, and they had like a demo that they were using glitching to bypass the U-boot protections on some vendors. And they also gave some this talk, 20 ways past secure boot. It's really interesting, not only U-boot, but targeting embedded devices in general. And there's also this group called Aleph Research. They have lots of bootloader bypasses, but they're more targeting mobile phones. So it makes sense for example, mobile phone companies. They don't want you to like root your device and put like crap because you might break your device. And also like video game companies as well, like Microsoft, also like Sony. They don't want you to jailbreak your console because you might run pirate content. So they like the bootloader from those devices, they're very secure. And nowadays people are starting to research on those bypasses so they can boot unsigned code and do wherever they want. But nowadays for like home routers, for like embedded devices in general we have at home, there's no protections at all. So it's like a huge difference from those devices and like the devices we have at home.
4 minutes.
So yeah, some firmware security resources. There are like some websites showing how you can use TPMs to protect your validate. For example, if you have a BeagleBone Black, you can buy capes, and it's like that acts like a TPM, so you can have like secure boot on your BeagleBone Black. There's also this really interesting book from Intel guys and some other researchers. It's called book Rootkits and Bootkits. And there's also a firmware security training from the Intel guys, which is open source. It's on GitHub. For example, they dissect the UEFI bootkit from hacking team. They show how you can detect that. It's also really interesting. So conclusion, secure boot is important nowadays, also for embedded devices. And we have to reduce firmware opacity, which means that not only tamper-proofing, because vendors, they care too much about tamper-proofing. They don't want us to like change things, but they also don't give us ways to like verify if what we're running is the actual device that's supposed. So in the NSA case, what if NSA intercepts something? How can I verify? So like there are ways like DMA or like, I don't know, if you can plug something that's going to show a QR code. Vendors are not giving us like easy ways for us to verify our devices. And
also, physical impediments, like having a jumper on your motherboard, like in the good old days, have it on your embedded device. It's an issue for vendors because it just costs money, or having a bootloader on a separate flash chip, it's too expensive for them.
Chromebook.
And but a Chromebook has on the right pin, in order to write to the Chromebook flash memory, you have to actually loosen a screw to be able to flash the bootloader. So Chromebook is doing this. Is doing this well.
This is really interesting because the right protector is enabled, so you have to physically remove something. So we also need better like reverse engineering efforts on bootloader because people don't care about like the U-boot partition. We need better parser. We need like better research on this area as well.
I guess time's up.
Time's up. Like questions.
Let me get you the microphone.
Sorry.
what are the different ways to get into the U-boot? So I heard you saying that you were connecting through UART, was it? Or
Yeah, you can go through UART. Yeah,
is it
one of the
can you go
methods.
through JTAG as well?
Yeah, if JTAG is on the board, then you can also use JTAG.
What if the IoT device is completely like fucked off those two connections?
Sorry, what?
Well, what if the manufacturer's like gone on the board and like removed those
Yeah,
connections?
then you can dump the flash. If you have a root shell on the device, you can dump the flash from there and dump also the
So
U-boot partition.
you'd have to get root on the.
Yeah, if you have root on the device, you can usually get access to the partitions.
Okay. Okay. Thanks.
Hi. Was this research done in the context of KPN or generic your own investigation or?
So yeah, we work for the red team. So we work for a telco, and telco has like network equipments. So we do test a lot of hardware for the company. So yeah, and we do this as like an additional layer because malware targeting embedded devices nowadays they don't care about persistence, but there's going to be a day that hacking embedded devices is going to be more difficult, and like they start thinking about persistence in the firmware level, and after that on the bootloader level.
But this was a project, yeah, we did it in your spare time, basically.
Yeah, so it's like we do that as like we have a toolkit. So if we're doing red team engagements, for example, we put an implant in the network, and then we have this dual boot thing so it's more difficult to detect. We also have like in-house tools for us to test as well.
Okay, thank you. More questions? No?
Okay, that's it.
Okay, that's it.
Thank you.